cred că, din păcate, situația nu-mi permite să intru într-o introducere corectă, așa că voi începe din start cu carnea lucrării. O voi prezenta în engleză, apropo. So, basically, in space, there are two main challenges regarding temperature: how we can keep it constant and how we can get rid of excess temperature, or heat would be more correct. Let's start with insulation. In space, there are two main methods currently of insulating: aerogel, which is a very light material comprised of mostly air, which has a remarkably low thermal conductance, and multi-layer insulation, which is currently used on most spacecraft. You can say most satellites and most remarkably the ISS. It's usually comprised of three layers, all aluminized to reflect radiation and heat. One polyester, one aluminized polyester, one Kapton, and one mylar. They have special properties which I cannot really get into right now. The point is that in more complex situations, the best way to go forward is by mixing them. For example, a study was done in about 1998 that showed that by combining aerogel and multi-layer insulation in a certain way, we could use aerogel's performance in low vacuum situations and MLI's high vacuum performance to get an optimized performance regardless of the conditions around. As you can see, 40 layers of MLI are all around the lowest thermal conductance. But by combining MLI and aerogel and then another layer of MLI, we can get a somewhat less overall performance in high vacuum conditions. But if conditions were to degrade, it would be better. It wouldn't compromise MLI or add the aerogel. And also the aerogel also serves to provide somewhat of a structural support to the somewhat feeble MLI because layers are very small, basically. Now that we know the basics of keeping heat in, let's worry about getting excess heat out. Of course, if we have a situation like the ISS, we have people on board. People generate heat. That's just what they do. So we need a way to get that heat out because it's not going to go out because of the insulation, so we have to have artificial methods. Heat rejection has two modes: passive and active. Active is just building on the passive methods. The best way that we have found up to this point is by using heat pipes. Basically, these pipes have three sections. One was a place where they intake the heat from the environment, an adiabatic section which just passes it through, and an outtake section which radiates it forward. These heat pipes can be laid throughout a set of space settlement or a space station, and then connected to radiators, which function using the Stefan-Boltzmann law. I have found that carbon-carbon composite heat pipes have several advantages due to their, one, lightweight material, and two, remarkable heat transfer properties. And they function well at almost any temperature. So basically, the material of the pipe isn't the bottleneck, the fluid is actually the working fluid which passes through. There have been several approaches tried. ISS uses H2O mostly because there aren't that many people on board, so they don't expect a huge temperature. But I have found that using carbon-carbon composite heat pipes, we can even use cesium or potassium. Cesium has some disadvantages due to its high viscosity, but potassium can function efficiently up to temperatures of 700 Kelvin, which is huge if you know the Stefan-Boltzmann law, because then you know that the energy that can be radiated depends on the temperature to the power of 4, which is huge. So essentially, potassium, due to its low viscosity, low vapor pressure, and all around higher specific heat, works amazingly as a fluid in carbon-carbon pipes. Actively, we can build on said pipes and radiators by introducing controlled thermal regulation, which are essentially just huge systems of pipes that run throughout the complex, which have mechanical pumps to redistribute heat where need be. So essentially, you don't necessarily just outtake heat to space. You can also redirect it to other parts of a space station if need be to insert more heat. You can take it from the electronics and the engine bay and then redistribute it back to the people, or just radiate it out as need be. After that, we can tackle the radiators. On radiators, if they are left empty, they will just radiate constantly at the set rate. But if we use louvers, we can control their emissivity by changing the angle. Of course, putting a louver on a radiator takes down its baseline emissivity, which is usually 0.85, because the blades aren't infinitely thin. If we could make a louver that has infinitely thin blades, we could use them without any drawbacks. But we can't, so we have to compromise on the emissivity of some of the radiators to allow ourselves to have a major control over how much heat we actually want to disperse. Essentially, if the temperature is correct in the space station, we can shut down the radiator effectively by closing the louvers, and vice versa. Now let's look at a case study. I think the best way to show how we can use these technologies is to actually look at something that might be done by civilization in the somewhat near future. I proposed a space station, space settlement near Titan. There were several reasons for this. One, Titan is far away from Earth, so the heat from the sun can pose a challenge. Two, it has a very dense atmosphere, which also emits heat, so you don't necessarily get high vacuum conditions. And then because of its distance from our planet, we can get away with having a high population of 30,000 because we need to have industry, we need to have self-sustenance. And so all of these factors lead to a huge heat generation, which allows us to properly demonstrate the true efficiency of these methods. Now let's take a look at some of the heat sources. Humans generate part of the heat through their bodies and through their day-to-day activity. Using metabolic units and the Duboskin area, we can find that the human can, at any point in time, generate up to about 384 watts of energy. And looking at some real-life statistics on Earth, we find that humans per year consume about 22,000 kilowatts hour, so about 2.51 kilowatts. Using this and other heat sources such as industry, farming, and engine bay operation, which due to the large amount of energy uses of factories and farms today, we can approximate to be about 350% of the heat produced and consumed by humans. Yeah. So using all these factors, we find that we would have to disperse a heat of 390 megawatts. Well, this is a huge amount of heat. To even grasp the concept, we will need to look at nuclear reactors, which produce about 7 times that. But in a reasonably small space, that's a lot. So using the Stefan Boltzmann constant and the methods I've proposed earlier, we can actually find that we only need an area of about 32,760 square meters to actually disperse of all that heat if everything was running all at once. Which is actually a surprisingly low amount of space compared to the insane amount of heat generated. So to keep it short, in conclusion, in space we need to balance thermal loads at any point in time. We need to learn that materials can be used in different ways than initially thought, and they can have higher efficiencies than classical methods, which have the heritage factor. And the importance of thermal regulation, of course, is a critical factor in the viability of future space settlements and the survival of mankind in space. So in conclusion, again, efficient thermal management is based on various components, which thankfully we can control and improve at any point in time. Thank you for your time.